So that's still possible?
So if you got a 55,
get a 55.
You would lose 9.9% of your grade.
Yes.
You could even go lower.
But then you could never lose another point.
Yeah. You could never.
No, let me make it clear. So again, you get the maximum of whatever the syllabus says and what I think. And certainly I think that if you get a 55 in the first test and ace everything else, you're getting an A, for sure. Right? Because that includes the final, which is absurdly difficult. Okay, so only because it's everything. Only because it's not because I'm making it difficult, but it's because it's everything we ever talked about on one test, and you have 2.5 hours, and I give you an hour and 45 minutes for each test, and you only have 2.5 hours to do all of that. So that's what makes it hard. You have to do it all in that short amount of time. I'm not making it. I don't have to make it difficult. It's difficult on its own. Okay. So, but if you ace that, then that goes a long way. But then usually what happens is that people just cruise their way through that test. But a lot of people also need to redeem themselves. I thought I had the test here somewhere. So, did anyone see it? Calc 2. Oh, I think it's right. I don't see it. Let's do this. It should be right here. Oh, no, I don't want to do that. All right. I'll take questions about any of these. I'll answer whatever questions you have. If you need answers to any of these, let's cover them now. As the test come around, does everyone have a copy now? If you don't have a copy, would like a copy, it should be right there next to you. Okay. If you want to, again, if you want to go over this stuff one-on-one, I can go through each problem with you. And now I'm here on Wednesdays. 11 to 2 on Wednesdays. So you're too happy about that. I was enjoying being at home, sir. I was. Until people in the other class said, can we meet? There's no Mondays. This Wednesday. Please.
No Mondays.
That's right. No. So I've already been thinking today how I'm going to tell my wife that I'm not going to be at home from 11 to 2 on Wednesdays. Okay, so.
Wait, you said the other class was a
77.
But I thought their days are split up. Like, we only have one day, so how's that possible?
And the bad part about this is that the video from earlier, I did not have the record button. This here has to be red, and it was green the whole time for the first class. And so I was going to let them watch this video instead, but now I can't because you keep talking shit about them. So now, I mean, yeah. So now they just won't have a video for the week, or now I have to edit it out. Now I have to do so much editing. Yeah. Exactly, and then they can find it on my feed. That's exactly right. That's right. We need to start over again. That's right. I start over like, hello, welcome. Section 2 is fantastic. I'll just start by saying that.
Is there a pause button?
There is no pause button actually. Like you go here and it's either, it's stop or restore the window. I can restore the window, but I cannot stop it. So. Without it just being done. So, yeah. But listen, we talked about that. You all, very focused. I mean, you all work all day, most of you, right? And then you have to come here for 3 hours. So, clearly you're motivated. So.
Or more if we have a lot of people.
That's right. So credit to you all, for sure. So as I said, if you want to go through any of these, any pressing thing, you let me know. But again, yeah, it's going to be this. And so this problem here is a microcosm of how I am. 7. There's a formula. There are ways to do things with the formula. I ask you to write the formula. You do that, and then I ask some conceptual thing about it. Okay. And so a lot of people got B, and so I'm going to be asking, and this didn't used to be the case, but there's some things you're going to just have to know how to do step by step. You're going to have to know how to integrate. You're going to have to know how to take the antiderivative. But you're going to also have to know, what the integral means, right? So concepts, and you need to know the mechanics, right? And let me say, it used to be, and a lot of my colleagues still only do mechanics. Can you integrate, right? But then what happens is you get a lot of people who crush the AP, calculus exam, but have no idea what a derivative is in 3 words. What in the world is the point then, right? So you got people who can integrate, have no idea how to explain the definition of the integral, but they can integrate anything, but don't know what it is, right? That is completely pointless. So I'm definitely doing both, right? So this is why number 1 on every exam is this question, on every exam. So number 1 is already taken for the next exam. It's always going to be this. Define the integral and state the fundamental theorem of calculus. Okay, and then everything else changes, but that's it. Okay, but if there are no questions about the test, we'll just move on to chapter 7. Okay. Again, I'll take your comments and criticisms. I'll welcome them for that test. I think I had too much fun with it. Okay, but apparently you did too. So we both won there. Chapter 7. In chapter 3, at least here, chapter 3 for Calc 1 is all about the derivative and mechanics. Okay, so the chain rule, the product rule, the quotient rule, the derivative of trig functions, the derivative of inverse trig functions, all in chapter 3, all building up to being able to use those applications in chapter 4, where you find the maximum value, the minimum value of all of these functions. To mirror that, chapter 7 for us is all about the antiderivative and all the different ways of trying to find antiderivatives. I've been kind of slick over the last few weeks, right? No one's actually called me on it, but we've been taking a lot of integrals of a lot of different things, but no one has asked me what in the world is the antiderivative of that. Thank goodness. Right? No, the derivative of the natural log is 1 over x. But we have never said anything about the antiderivative of the natural log of x, right? Or the antiderivative of the inverse sine of x, right? We've been talking about what's the derivative of that. So we need to figure this out. Only because, again, the natural log is just such an important function, right? So the natural log doing like this, right? It's one of those functions that models so many different things, okay? At some point, clearly, might we want to know the area under this damn thing? It makes complete sense. In order to do that, if there's any justice, we would like to find the antiderivative of that in order to find the area. Okay, so in order to do that, we're going to integrate by parts, right? This is section 7.1. Then there are a ton of methods, and let me just say, hold me to this, it's on tape. If 10 years from now we're still teaching like this, then I'm going to retire. Okay. Again, just like in chapter 3, learning these archaic methods, when we have devices that can do all these integrals in seconds, we really need to change the way that we teach Calc 2. I am a firm believer in that, but I'm still a part of this bad system. So this is what we're going to do. Okay. I know that's great motivation right now for this chapter, but I'm just telling the truth, right? And I said the same thing for chapter 3, for Calc 1, I'm pretty sure, that spending all this time learning all these derivatives, when you become an engineer, you just, you're going to get integrals, obviously, when you're an engineer. It's unavoidable. You're going to get triple integrals. But then your firm will have Mathematica and Maple out of the ass, for sure. And you go type it in, and they give you the answer. I mean, that's just how it works, okay? There will be times in which you will need integration by parts. I mean, you're working through some integral, some model, and you'll have to integrate by parts. But a lot of this other stuff, it's good for the idea, but you will not be doing these things by hand, only because The problems that you do modeling reality are so difficult that, I mean, it's just the integrals you come across, you won't be able to do by hand anyway because the functions are so complicated, right? The point being that, again, this is why, in some sense, my tests aren't so difficult, because any real integral, why would I make an integral in a test so difficult when in reality you would never have to do it by hand to begin with, right? So that's why I'm looking for, you know, just conceptually, do you understand what's going on in the antiderivative process here? I am just having a mathgasm about 7.8. I cannot wait until we get the differential equations, because that's some real applications. We'll do some stuff there. But 7.1 through 7.7, we'll make up the bulk of the test, obviously. And again, it can just be one question, and it's that find the antiderivative. I mean, that's basically the question. Number 3 on the test is find the antiderivative 4, find the antiderivative 5, find the antiderivative 6, find the antiderivative, right? They're just all different methods of doing that, right? After we do chapter 7, then it's chapter 8 and 9 for test 3, and that's the last part, sequences and series. And then by that time, the class will be over. I'll take any questions about where we're headed. Again, we're doing all these antiderivatives because they help us do integrals, okay, using the fundamental theorem of calculus. Right, all of that stuff, that's right. We gave a hint to that last time. All right. Here's what we know. We know how to do this one, right? We're experts at this now, right? 3x squared, the sine of x cubed, right? That's an easy one, right? So we're going to do this by substitution, right? Let me also mention that we're in chapter 7, and chapter 7 has nothing to do with work or volume or rotate, has nothing to do with any of that stuff. So literally, deep breath, we're starting all over again, blank slate, right? So it's like the beginning of the class all over again. The question now, of course, is how do we now do this one? Right? And just by looking at it, this one looks easier, but in fact it's harder. Simply because you cannot substitute. Okay, so what makes this hard is that we have two functions that are in two different families that are multiplying each other, and that will be what gives away that we're going to integrate by parts. Right, so integration by parts. On the exam, I'll say, find the antiderivative by integrating by parts. Find the antiderivative, you know, and it'll be obvious that you'll have to do some methods because they'll be all trig functions. I'll say find the antiderivative, and it'll be obvious because the forms in which you do trig substitutions will be obvious too. I will say find the antiderivatives using partial fractions. Right? On the final, I won't say any of that. There'll just be tons of integrals, and you have to know which one to use when. Okay. So what I'm saying about integration by parts is you know to use integration by parts when you have functions from two different families multiplying each other, and you cannot substitute. Okay. If you can't substitute and you have a polynomial times a trig function, you for sure are probably integrating by parts. Okay. Now, to be in tune with the way things have gone in class, every single antiderivative rule has had a corresponding derivative rule. For example, the substitution rule for antiderivatives was analogous to what differentiation rule? The chain rule, for sure, right? And in this case, integration by parts is analogous to, you know, the product rule. Really good. Let's demonstrate that. Okay, so let's derive the integration by parts formula. It comes directly from the product rule. The product rule, we know, says that the derivative of u times v is u prime times v, I really like that, it's v times u prime plus u times v prime. That's just the product rule. Our notation we've been using, we'll use Leibniz notation. This is v du plus u dv. And what we'll do is now we'll take an antiderivative on both sides, right? So antiderivative on both sides. And then hopefully you can see, well, the antiderivative of the derivative of uv is simply uv, right? So they cancel each other out. And that's equal to the integral, or the antiderivative of v du plus the antiderivative of u dv. And it is this thing that we typically solve for. Okay? And so the integral of u dv is equal to uv minus the integral of v du. I simply brought this to this side, okay? And changed the sign. That's the integration by parts formula. Again, coming directly from the product rule. And on the test, I'll say, prove that for extra credit, maybe. Right? I'm hinting towards that. I should say I'm leaning towards that. Because the derivation is not that difficult. I mean, you literally write the product rule and integrate on both sides. Okay. And so, immediately you should say, okay, you've given us an antiderivative formula, but the damn thing involves another antiderivative. Why would I? What's so nice about that? The hope, of course, is that this antiderivative is way easier than this one. Okay. Let's apply that. Let's see if that works to the one that I had mentioned. The antiderivative of u dv is uv minus the integral of v du. And so for us, the antiderivative of x sine x dx. All right, so here we're going to pick a u and a dv. So again, what is the formula saying? It's saying that if you come across the product of a function and the derivative of some other function, then you can rewrite that antiderivative as this if you so choose. Okay. Here is that case. So I have a function times the derivative of some other function, right? But of course, both of these are derivatives of some other function. So we have to make a choice about what we want u to be and what we want dv to be. Okay, so let's put that in red. So we have a choice. Right, so we can choose u to be x, dv to be, and I'm going to use Leibniz notation the whole way, so sine x dx, or I can choose u to be sine x and then v to be x dx. You'll always have this choice, okay? And we're going to come up with some guidelines on which one should be u and which one should be dv. Which one should it be in this case?
dv equals sine x or is it equals v?
I'm sorry, dv is sine x dx with the whole notation.
I mean, you have u and dv.
I'm sorry, this is dv, I apologize. You're absolutely right. Okay. Which one?
You try the first one.
We'll do them both. All right? We'll do them both and see what happens. Okay. So we'll go ahead and call this 1 and 2. Okay. So this is 1 and this is 2. So for 1, again, we have the antiderivative of x sine x dx, and hopefully, if I've done this right, and I have not, I have the nice one first, but that's okay. So this is the one we should do, and hopefully we can see why pretty quickly. So if we let u equal x, actually this is a good way to do it, and dv be sine x dx, then immediately, let's go ahead and put the formula again. The formula is the antiderivative of u dv is uv minus the integral of v du. The over-under on the number of times I say that tonight is about 27 and a half. Okay? And I'm taking the over. Right? So I'm going to be saying this a lot. This, of course, requires that you know this like the back of your hand. Question number 3 on the exam is going to be integration by parts. Okay? So question 1 being the definition of the integral and stating the fundamental theorem of calculus, and question number 2 being about mass and work. Okay? You thought you would avoid that? Okay. Looking at the formula, in order to fill out this formula, I need v and I need du. Okay, so du equals the derivative of x, or again using Leibniz notation, that's dx. And if dv is sine x dx, then v is simply the antiderivative, and in that case it's minus cosine x. I'll take any questions on how we got those two. Right. So again, to fill out the formula, I need more than just this. I need the consequences of this. Okay. So you take the antiderivative to get v, and you take the derivative to get du. I hope that's obvious. Let's just use the formula. uv x times cosine x with a minus sign, minus, I'm sorry, yeah, that's right, minus the integral of v, which is minus the cosine of x, times du is dx. And the question, of course, is this integral now easier to do? And it is.
Can you do it multiple times?
We will. We will. And this is equal to, I need to put equal signs here. This is equal to minus x cosine x, and then the antiderivative of cosine is sine, and that is the end of the game. Remember what we're doing. We claim that, and we're pretty confident, that the derivative of this is this. And hopefully you can see how it comes from the product rule. When you take the derivative of this, obviously you need to use the product rule, but this one term through the product rule creates how many terms? 2. This is only one term. So obviously I need something over here to cancel out that extra term so that I'm left with one thing. Please. Is that okay? Okay. Questions about this? Let's do it the wrong way, or the other way, the more complicated way, however we want to say it. If instead, we had x sine x, and so then we're doing it the second way, and we say, well, okay, let u equal the sine of x, and dv equal x dx. We have that choice. Then the integral of udv is uv minus the integral of v du. Then from this, an immediate consequence, of course, is that du is cosine x dx, and then v equals 1/2 x squared. Already looks more complicated, doesn't it? uv minus the integral of v du, 1/2 x squared times the sine of x minus the integral of v, 1/2 x squared du is cosine x dx, and for sure that is more difficult. Questions about this? When you can, if I did this first, I would say, okay, clearly I've done this wrong. I need to do something else. Okay? So how do you know which to pick? And it has to do with derivatives, right? So, all right, being a dead horse, not dog. We have this again. Then it has something to do with derivatives, right? So really the question is, how do you pick u, right? So I've decided to only focus on U. If we know how to pick U, then DD is obvious. That's the other thing. Okay, so we were talking about families of functions. We're multiplying families of functions. Right? And then for at least for U, we are taking derivatives, and then the derivative does something to this family. We pick U, and I was saying that if you pick U, U becomes du over here. This is why I'm interested in taking the derivative, and then you get a different family potentially. And so here's another family of functions. I want a real arrow here. Let's do that. Okay. So give me some families of functions that we have. So we have some trig. Okay, so let's write these out. So we have some logarithms, we have logs, we have inverse trig. We have indeed, we have algebraic ones that just involve x and powers of x, right? So we call those algebraic. And then we have trig functions. And what's left?
Rational.
Oh, we make those algebraic. Exponentials, right? So again, it's a serious tragedy that we have a book entitled Early Transcendentals, and then the author never mentions what the hell transcendentals means. Okay, so but transcendental numbers are numbers that are not algebraic. That is to say that they're not the coefficients of they're not solutions of integer coefficients of quadratic or polynomial equations. That's a complicated way of saying that they're not. They're very, very irrational numbers. Okay, transcendental numbers. There are two transcendental numbers that pervade all of calculus. What are they? E and pi for sure. And as you can see, they're the basis for 4 out of the 5 functions here. And that's why we call it early transcendentals, because these are the 2 earliest ones, and the functions that are derived from the other transcendentals are off in some other place, and we don't talk about those in Calc 2. Okay? But obviously, E is the basis for the exponential, and this is simply the inverse of that. And pi, of course, forms the basis for the trig functions and the inverse. Okay? That's why the book's entitled Early Transcendentals, because 4 of the 5 functions depend on these transcendental numbers. Okay?
We're doing hyperbolic. Or is that later?
Right, so hyperbolic sign is what? Define it for me. What? No, what's the hyperbolic sign? Okay, the hyperbolic sign. Look it up. Look it up. It's in the book.
Cosine, or it's sine h of x.
No, that's the hyperbolic cosine.
ddx of sine hx.
No.
It's cosine d hyperbolic cosine.
Yeah. What is the hyperbolic sign?
E dx minus d to the negative x over 2.
Over 2. That's right. But that's already a what? What is that here? That already fits into one of these categories. Those are just exponentials. Yeah. So they are already been covered. Yeah. So that's right. But those are really important. Obviously, they're so important they have a name. So clearly they're important, and they're used a lot in engineering for sure. Right? But from the mathematical perspective, they're just exponentials. Right? Through the derivative, so for example, the logs, 1 over x, the natural log of x is an example, and through the derivative, it becomes what?
Algebraic.
Absolutely, 1 over x, which is algebraic. That's absolutely right. So that becomes algebraic. Through the derivative, inverse trig, let's put our favorite one, right? The inverse sign of x, inverse sign of x. What does that become?
1 over the square root of 1 plus, what, 1 minus?
Yeah, minus x squared.
Right? And which family is that? That's also algebraic. Okay. Algebraic, the derivative of x squared becomes 2x, so algebraic goes to algebraic. Okay. So right now we're talking about the derivative operator. What space does the derivative operator take functions? Okay. So this algebraic functions are closed under the derivative operator. Right? If you're algebraic, you stay algebraic. I'm claiming these are closed too. Take a trig function like sine. Take the derivative of it, you get another trig function, right? That's cosine. So trig goes back to trig. And sine and cosine are twins in that way, I should say siblings. Because, of course, you keep running through the derivatives for sines and cosines, and you just get more sines and cosines. What other functions are twins like that?
You wrote algebraic.
No, in terms of trig functions. What other trig functions are twins? Sine and cosine are. What are the other ones? Secant and cos. No.
What is it?
Secant and the other one. What starts to show up? Tangent for sure. Derivative of secant is secant tangent. The derivative of tangent is secant squared. You just keep taking derivatives of those, right? You get tangent and secant all the time, right?
But you wrote algebraic.
Oh, I'm sorry. Yeah, that's just wrong. Right. So it's trig. And finally, exponentials are closed. We would hope that there's an injustice here. E to the x, right? And so here, exponential. Okay. Why is this important? This is the order you should pick u. This is the order. Okay. So you should pick u in this order if these functions are present. Why is that? Well, we want this to be easier, right? And we've already said that algebraic functions are easier than all these other ones. So if we have the opportunity to turn a log into an algebraic, or turn an inverse trig into an algebraic, we should do so, right? Because they present problems over here if you don't. Right? If you call this dv, then you're talking about taking the antiderivative of the natural log of x, and we don't even know how to do that yet. Okay. So that's the order. We'll go ahead and extend. U should be picked in this order. We'll put it in green. U should be chosen in this order. You can switch the first two. It's not that big of a deal. If it helps you remember it, however you remember it. I'll take questions about that. But it's simply because that you go into a very nice family through the derivative, and that helps us. Okay. Oh, sir.
You say you can switch the first two. Do the bottom two matter much, or just
Not really, yeah. Not really, yeah. I mean, again, we're going to do e to the x times sine x, and it's just an absolute pain. So much so that I'm going to give this extra credit. So, I mean, it's just integrating e to the x times sine x. First of all, if you can't substitute, and it's going to be really difficult to substitute that, right? Because if you want to let u be one thing, and then the derivative clearly is not going to be an exponential, right? Because they're not in the same family. Okay. So, you know, when you do that one's just going to take some time. So, other questions about this? Let's finally do the one we have. Oh, we did that one. Let's do another one. Let's do x natural log of x. The antiderivative of x, the natural log of x, dx. Number 3A on the exam. Pick a u. Technically dv. Pick a dv. I think it's x natural log of x minus 1/2 x squared or something like that. so awake. Usually I'm just like out by this time. I have no idea. I better knock on wood now, right?
So in this case, it doesn't matter which order you pick them.
No, I think that you can switch the top two and the bottom two, but I would certainly pick a log over an algebraic. U should be the natural log of x. So if you're picking U, so you have an algebraic and a log, and L comes before A, so you pick L. You want U to be the natural log of x, and then dV is x. Yeah. So for that, U equal the natural log of x, dV equals x. And so I'm going to do that in parentheses. As a consequence of our choice, then du is 1 over x dx. V is 1/2 x squared is the antiderivative, and we flat out use the formula. uv is 1/2 x squared, the natural log of x, minus the integral, and we hope that this is easy now. V is 1/2 x squared times du is a nice algebraic thing. And so now that natural log that was in the antiderivative sign completely gone, and we are now salivating over this one. It's 1/2 x squared, the natural log of x, minus the antiderivative of 1/2 x dx, and this is not a problem. Minus 1/2. I'll hold that 1/2, and then another 1/2 appears from taking the antiderivative, invoking the power rule, and that is the game. I'll take questions about that. We'll do some multiple ones now. We have to do more than one in one problem. Not my intention to give any like that, but I do want to show you that that can happen. But I'll take questions about this. All right, let's do x e to the x. X e to the x. All right, practice, distance, practice. X e to the x. See, now I'm yawning. See, I'm crashing now. I was excited. I was running around earlier. I should have paced myself. dv d to the x dx. As a consequence, du is dx. D is the antiderivative of e to the x dx. And again, we got to know that. That's e to the x. What am I doing? How did I write this already? So we're talking about u times v x e to the x minus the integral of v. Let's hope it's nice. E to the x du dx x e to the x. The antiderivative of e to the x is just e to the x plus a constant. I did that to set up this one, okay? So what about x squared e to the x? Let's do that one. This is the one I really wanted to do. We'll do a couple more. I guess I'll do a definite integral. I want to know the area under one of these curves, okay? But I mean, the fundamental theorem of calculus just tells us that we need an antiderivative, and we just plug in all these endpoints, okay? But you can imagine a problem maybe if you have like a hyperpopulation in biology, right? Where instead of the exponential, you might need x times the exponential instead to measure its population increase. Okay, so what happens in biology is that we always assume that the rate of increase for a population is constant. What if it's not? What if it's not constant? And so then your population increase is not just e to the x or 2 to the x. Maybe it's x times 2 to the x. And maybe you need to know the area under that curve, right? That requires that you integrate by parts, for sure. So you can imagine that the functions that really model reality are a massive combination of products of all the functions that we have. As a matter of fact, I mean, obviously the e to the x times the sine of x is an important one, right? So if we, how's Maple not already open?
Yeah. Is it 0?
Is what 0? You're giving me a number, and I'm asking for infinitely many functions, right? So I want to know the antiderivative of this. How do you get 0? Right. So let's go ahead and do this. What's u? Yeah, u is x squared. dv is e to the x. Listen, I mean, u could be x to the 5 million. I'm still going to pick that damn thing over e to the x. Okay, it's just that simple. dv is e to the x, and the reason's right here, right? du has now made that much simpler. V is staring us right in the face again. I mean, it's just nothing's happened to it. Right? uv minus the integral of v du. Have I written it on this page? I have. U times v x squared e to the x minus the integral of v du. That's right. So it's e to the x times 2x dx. And then we'll remark, well, okay, this is easier. However, in order to do this, I'll remark, first of all, I cannot substitute, but being the observant people you are, we just did this. Right? And so then you would have to do it again. Okay? And so this is equal to, thankfully, by luck, we've already done this. Right? So this is 2 times, and then from earlier, we have, I'll put it in blue, x e to the x minus e to the x, and I'll throw the constant on the outside. The constant being arbitrary, if I multiply it by -2, it's still arbitrary. Right? And then you have it. So sometimes you're going to have to do it more than once. Again, I don't envision, maybe in my math lab I'll have you do it 35 times, but on a test, you know, who cares, right? So. Questions about this? But to make the point for, you know, functions modeling things, let's look at the function f that assigns x to e to the, I'm sorry, e is called the exponential in Maple, so e to the minus x times the sine of, let's go ahead, of 10x. Let's do that. All right. And then I want to plot f, okay? So then I want to plot f on the real line, ploy, right? Plot f of x, and I want x to go from 0 to 10 is good enough, 0 to 10, right? I mean, so we already have it, okay? So, I mean, this clearly models someone who goes bungee jumping already, just the bouncing, right? And then eventually they just level off, right? So you need this. Right, assuming that it doesn't break, that's right. But they level off at 0. Of course, we can add, you know, 5,000 to this to put it at whatever height you're jumping from. But the bottom line is, and why don't we just do that? So we add 5,000 to this, right? So we're at 100, right? Plus that. You know, something like this, right? And so then it levels off at 100, okay? But, and you can see that this is, you need this for sound waves, all of these things, right? Obviously, you need to be putting these functions together in order to get functions to model what's going on in real life, right? So we just can't, we've been playing around with the baby integrals, right, earlier on, okay? So we need to deal with the complicated ones too. Okay, questions about this? Again, I don't envision having you do this more than twice. Right? And I mean, if I have you do it 3 times, it's for sure extra credit. Because it's just tedious. Let's just go ahead and do the natural log of x. What in the world? What's the antiderivative of that? All right, so I've been hiding this from you, right? And only taking derivatives of that. All these other functions we can take the derivative of and the antiderivative of. The trig functions, the exponentials, no problem. But this one, we have not done yet. Let us do it now. Right, so one function here, right? So, but it's 1 times the natural log of x. Right? So 1 is algebraic, and so again, you should pick u to be the natural log of x. Use the natural log of x, and then dv is 1 dx. Okay. So if you only have, if you see one function, then you can always make it 2 by saying that one of the functions is 1. Use the natural log of x. dv is 1 dx. As a consequence, du is 1 over x dx. And v is x. And when you go through this, you'll see why we don't make this one of the ones you have to memorize, because it's not one of those easy ones to memorize. But you do it enough times, you'll remember it. That should be, I think it's x natural log of x minus x or something like this. We have u and v given. This is x natural log of x minus the antiderivative v is x du 1 over x dx. This is equal to x natural log of x minus the antiderivative of 1 dx. The function whose derivative is 1 is x. What's a constant? Again, you can check that. Taking the derivative of x natural log of x with the product rule, you get x natural log of x plus 1, but then that plus 1 cancels out with a minus 1 you get when you take the derivative of negative x, and you're just left with x, the natural log of x. Questions about that? So we're going to do inverse sine, inverse cosine. Let's go ahead and do inverse sine now. What's the antiderivative of inverse sine? We'll do the same thing. We've been taking derivatives of that time and time again. And remember, inverse trig functions, we were using inverse trig functions just to measure, how tired we got in this class. Remember, we used the inverse tangent as a way of modeling how, after a certain point, the law of diminishing returns kicks in, and we don't gain that much more. The derivative is so much smaller as we go along in this class, right? We learn the derivative decreases as the time goes on. The rate at which we learn decreases. So u is equal to the inverse sine of x. dv is 1 dx. This one's a little bit trickier, okay? u is inverse sine, dv is 1 dx. As a consequence, du 1 over the square root 1 minus x squared v x d, x d nothing, x. Of course, the integral of u dv is uv minus the integral of u du. That's got to be like 15 by now. Times I've said that. We're going to substitute in, and of course, the whole goal is this antiderivative easier? Is it easier? Right? So the goal again is this. Is this easier? Right? That's the question. uv, x, sine inverse of x. Oh, wait, I need to see the book. There might be a ton of extra credit in the book, in the back. Anyone have the book? Have the book here? I'll take a look. Because a lot of those formulas in the back, the absurdly difficult ones, come from integrating by parts. So I'll take a look at that, see what we can get out of that. X inverse sine of x minus the integral. V is x. We'll do this for the moment. X times du. I'm sorry, there's a dx here, right? Notation, right? 1 over the square root of 1 minus x squared dx. Again, the whole point of this is this easier. Can we do this? How do we do this one? Right, you let u be 1 minus x squared, and then you do substitution. We'll do that in just a second. But again, for these problems, and I really like this one, okay? I like ones where, this seems like a part B, a part C for this problem, test question number 3, right? Part A is, are you breathing? Do you know the formula? Part B is, earn your A on this test. And then part C is something like this, where, you you use the integration by parts formula, but then it turns into something that we're already experts at and that you know how to do. So it's testing whether you're retaining, you know, some of the information. Again, the mathematics builds on itself. I'll take that separately. So for this integral here, we will have to substitute. We'll put it in blue. Substitute. U in this case is 1 minus x squared. Du is minus 2x dx. Why am I doing this? You all have this down. Minus 1/2 du is x dx, which is the thing we're substituting, and then we can substitute in. The antiderivative of x over, I'm going to put it together, the square root of 1 minus x squared dx then becomes the antiderivative of 1 over, well, x dx is minus 1/2 du, so let's just take care of that. Minus 1/2 du and then it's the square root of u. And this is just the power rule. 1 over the square root of u is just u to the negative 1/2. And then we'll use the power rule. So this is equal to minus 1/2, the antiderivative of u to the minus 1/2 du. We'll add 1 to the power and divide by it. It's minus 1/2 times add 1 to the power, that's 1/2, divide by it, it's 2. U to the 1/2 plus a constant. I am flying. I don't know, did I have a monster by accident or something? So minus u to the 1/2 plus a constant. All right, I just need to put this down. So I feel like most people would just get this. It's not a problem. Okay, so I'll take questions about it.
Did you leave out UV?
Oh, I haven't finished.
Oh, okay.
I just need to stop.
Okay.
I just try to rein myself in. So we're not done. I just need to chill out. Okay. All right, and then u is 1 minus x squared, and so this is minus 1 minus x squared to the 1/2 plus a constant. And now putting it all together, it is x sine x. Let's put it back in red. And finally, it's x sine x, and it's the inverse sine of x. X inverse sine of x. And then we need to be good with these minus signs, right? That minus a minus makes a plus, right? Because I use plus here, so it's plus 1 minus x squared to the 1/2 plus a constant. People ate up that extra credit, didn't they? That antiderivative one. I don't know if you can just go ahead and give another one, right? So, let's make sure that that's right. I think that's right. All right, let's go ahead and give that as extra credit. Show that this is the antiderivative of 1 over 1 plus 1 over the square root of, I'm sorry, the inverse sine of x. So for extra credit, this is probably the last time I can extend. This may get cut off, so extra credit. Take the derivative of this. To show that it is the inverse sine of x. Okay.
So wait, what are you going to use for?
Use the product rule on this, and then the chain rule on this, and everything cancels, and the only thing left over from the massacre is the inverse sine of x. That's the only thing that remains. Now, some of you, for the extra credit, just clearly put it into Wolfram. Okay, but I mean, and I didn't even want to even come to you and say, please tell me how you got this. Okay, but just make sure that you know the steps. They tell you the steps, okay? So, but make sure you understand the steps. Because I may put you under the spotlight, okay? But it's a good exercise anyway. I mean, I'm just happy that you see the steps. So I don't give a damn whether you put it in Wolfram or not. Now, what was that worth? How much was that worth? Was that worth 4 points last time? How much was that extra credit worth? You remember?
I know the highest one was 7.
Yes. No. Let's go ahead and we'll make it 3 points. Okay, this is 3 points really. All right. Oh, okay. Let's do. I'll take any questions about any of these. Is that okay? So it's the same procedure, right? So it's all going to depend on this integral, and the varying degrees of problems that I give all depend on the level of difficulty of the integral here. So that A, the integral over here is going to be easy. B is going to be slightly harder, and C, you'll probably have to use the substitution rule or some other rule. Okay. All right. Let's go ahead and deal with one like this, which is just an absolute pain. Okay. And then from this, I might give some extra credit.
You showed the bottom answer from the last slide.
Say it again? Oh, yeah. So, I think it's this. I think it's that. Give or take a sign somewhere. But that plus came from the fact that this was already a minus. And when I calculate this without the minus sign, I get another minus.
Yeah.
And so it makes it a plus. Okay. Are you questioning something else?
No.
Oh, okay. Okay, so this one here. And by the way, I mean, as we just demonstrated, unfortunately and fortunately, we need to know this damn one, right? The exponential times the sine wave. I mean, the only way to damp a sine wave is to multiply it by an exponential, right? In no way is the sine wave, the sine curve on its own really mimicking, sound waves, because, when a train goes by you, right, the sound it makes decreases in decibel level, right? So it's something like, it doesn't oscillate like this, but you can imagine that there's some things that oscillate and then become constant, right? There are, of course, some morbid examples, but, So, we do need to know this, right? All right, so, I don't even think it matters. But we'll make u equal to, let's say sine x. Let's see what happens. So that u equals sine x, dv is e to the x dx. Now, here's what I want you to know. We are looking for, and it's going to sound obvious, we're looking for that, okay? We are looking for this. We're going to do whatever it takes to solve for this. If we ever see this, we're going to solve for it. Okay? Okay, so we're going to see this multiple times, and we're going to solve for it. All right, so given that, du is cosine x dx. V is the antiderivative of this, is e to the x. I'll be giving extra credit in just a second. I may just have you do cosine, if it's not that much difficult, that different. Oh, actually, I'll probably use the back of the book to use one of their formulas. uv minus the integral of v du. E to the x sine x minus the integral of v du e to the x cosine x. I guess I can't give that one as extra credit because we're about to do this damn thing now. What you said? Nightmare. Yeah, you know, this is like a record. Like 3 days in a row, you said nightmare in Calc 2. Like maybe all of Calc 1, you said it like half a time. Like maybe you said nightmare. Like you could barely hear it. So now we'll integrate this by parts, and so the antiderivative of each of the x cosine x, we have to do this by parts. And the reason, of course, is we're multiplying two functions, different families, no way to substitute. We'll integrate by parts. So I'll make that note, by parts. Here, we'll let u equal e to the x. dv is cosine x dx. And I'll give you the game plan for this problem.
Would you still have to do it twice if you started with e to the x as u the first time?
Oh, let me answer your question first because it's easier. That it will repeat, and then when we do this by parts, another integral of e to the x sine x will occur, and we'll bring them all together. Right? We'll put them all together. Okay, and then we can solve for it. Sir, your question was? Okay. Okay. All right. So that now this integral on its own, uv e to the x sine x minus the integral of what? uv minus the integral of v du e to the x sine x dx. Okay? We just have to hope we have the right sign, and I'm worried. Okay? Questions about this? Oh, because I think we made the wrong, yeah, we need to switch these. Right? So we need to switch these, otherwise you're just going to get something that's true. Right? So u should be, let's make u cosine x. Right, so u is cosine x, dv is e to the x dx. Then this is negative sign, and I think that gives us the right answer, and this is e to the x. Let's see how that works. You're right, so yeah, if we did it the other way, you'd be going in circles, indeed.
If you start with e, because that's how I do it, and it's trickling down, or do you have to stay consistent with what you picked?
I think you have to do the opposite. Right. So here we picked the trig function, and now we're picking. Oh, I'm sorry. I meant to pick the trig function. I don't know why it switched all of a sudden. So I wanted to pick the trig function for both of them. Yeah.
Well, I accidentally did exponential. Should I keep it with that?
Well, what did you get?
I mean, I have it to where it's mining the integral of e to the x sine x, which is
Yeah.
no problem.
Right. Exactly. We don't want that. Yeah. That's because then you're running in circles. Yeah. So yeah, so you have to do it this way.
So
Yeah.
So if you see it repeating, you know that you're going to be wrong.
Yeah, that's right. Yeah, because you need to figure out what it is. Yeah. So yeah, and that's what happens. It's like, you know, the blue screen of death for a Microsoft machine. And so uv minus the integral of v du e to the x sine x dx. And I need a minus sign, right?
Just put it on the output.
Right, so it's plus indeed. Right, so it's, and I think that sign is right, and it works for us. So e to the x cosine x plus the integral of sine e to the x sine x dx. I think that sign is right. Okay. So then now, finally, going back here, we have, we'll put it in black. We have, yeah, we'll put it in black. We have e to the x. Go ahead and have space. Oh, I do. this now becomes e to the x sine of x minus this thing, e to the x cosine x, plus the integral of e to the x sine of x dx. Right? And so let's just make sure we know what we're saying. The integral of e to the x, the sine of x, dx, is equal to e to the x, the sine of x, minus e to the x, the cosine of x, minus the integral of e to the x, the sine of x, dx. Again, I told you to be committed to solving for this, and there are two of these. Right? And so we bring this over there. Right? We just add this to both sides. And so 2 times the integral of e to the x, the sine of x, dx, is e to the x sine x minus e to the x cosine x. And then you divide by 2. And so the integral of e to the x sine x dx is 1/2 times e to the x sine x minus e to the x cosine x.
The other way worked as well.
Oh, did it?
Yeah.
How? I'm looking forward to seeing that.
What do you mean?
And during the break. I'll take a look at your notes. Oh, yeah. Isn't that so obvious that I should go back? Let me see the book here. See if I can find something. Back here. Oh, these. Here we go. Okay. Let's see if we have some of these. No, what is this? Yeah. Yeah. Go ahead.
Which one was 7 page?
On the page after this? This here? I just divided both sides by 2. And then you divide both sides by 2, and the 2 goes on the other side. Right, so yeah, I'll take a look. Oh, here we go. Here's the claim. Extra credit. Prove the following. I'll give a couple points for each way. Now, you know it's bad when I have to sit here and read this damn thing. Okay, so it says, here's the claim. And it's formula, where'd you go? It's formula 49 in the reduction formulas. Okay, so formula 49. So prove formula 49.
What page is this?
I mean, they stopped counting. I mean, it's just on the back flap of the book. So, yeah, they're just like, we're done. Okay, so it says that the integral of x to the n times the sine of ax dx is equal to, and this is not going to be so bad, it's minus x to the, this is really a test, and can you just ignore these letters, or will the letters just scare you to death? Can you just not pay attention to these letters? x to the n minus 1, the cosine of ax. Let me put it under here. So I have a whole new line. It's minus x to the n, the cosine of ax over a, and then plus n over a times the integral of x to the n minus 1, the cosine of ax. And I don't think that this is too bad. A is a number, right? N is a number. Can we just work through it, right? If you integrate by parts, you pick u, you pick dv, and if you do everything perfectly, using the chain rule, making sure you multiply by a, divide by a when you need to, you should get that exactly. Even or odd? Even. Even. We'll make it work 4. All right. So I will go ahead and give you an extra. So I want you to prove this using integration by parts. So this is by parts. And then I'll go ahead and give an extra 2 points if you take the derivative of this and get that. Okay? And then for 2 points, take the derivative of this. Okay? It's a fire sale for extra credit. I got to get rid of it as quickly as possible. It's a going out of business sale.
So how we find the value for n and for n?
Oh no, they just, you have to pretend like they're numbers. So don't give them numbers. They're n and a.
For a?
Yeah. So for instance, yeah, you can. I mean, you can pretend and then put the a back there. But let's go ahead and
Make it 0 and call it a.
make it 0. Unfortunately, the book says that a is bigger than 0. I'm sorry.
Yeah.
Yeah. All right. So.
So in that case, how we find the value for a?
No, a is a. You don't have to just treat it like a number.
Oh.
Just treat it like it's a constant. Okay? And then it should work out. Okay? Let's go ahead and take a break there. When we come back, I think we're ready to move on. We'll come back at 8:05. 8:05. I'll take any questions about the test. If you feel like something's graded not fairly on your test, I will take a look at it. And my give back points is a pretty high rate. Oh, yeah. Oh, did you? Your name? Yeah, there you are. Sir.
This is the test. I just walked out without giving my extra credit. Is there any way that
Let's take a look here. Right, you're the one who actually had this one down from the start, so that's fine. Yeah, send me a, did I really make that worth 8 points? Wow. Send me an email to add in. Yeah.
All right.
Yes, sir.
I did it by saying EX.
Oh, yeah, so.
I canceled early because I got the initial negative cosine.
Right.
As the root. So it was VU, which is to see the x negative cosine that I was canceled. So I went and canceled now. Kept with the exponential is U.
Oh, so you just keep it the same both times.
Yeah.
It's going to work. That's pretty sweet. Okay, that's pretty. Oh, I thought you had done it cosine the first time.
No.
Okay, it was not the first time. Okay, fantastic. So flipping puts you in the endless cycle of death.
Yeah.
But if you remain, okay, that's good. That's good to know for the rest of the time. Oh, I'm sorry. Yeah, so, okay, so here's what we're going to do though. Here's what I want to do. I can easily add 15 and 20 to that. We need to be, and I'm going to ask you just all of the antiderivatives. Okay, and you've got to have them all. So we'll meet in a couple of weeks, But you come to me and I'm just like, what is this? What is this? I'm having to write them all down. And then I'll say, what is the antiderivative of this? What is the antiderivative of this? Okay. And having the cold, and I'm talking about, I'm sure you wrote the list in your notes. I'm talking about going through all the integrals. So the integral of e to the n, the integral of e to the n, the integral of sine, the integral of cosine. I'm just saying, like, that whole list, I'm sure it's in your notes. And then we'll meet and I'll just grill you. Getting them all right. Okay? Alright? It's just that simple. Sir?
Which one of these?
Yeah, so, yeah, I don't think so.
No, I didn't do, I did one with 5. There's one where it's like, through,
Actually, I do like that.
you did that, yeah.
I don't think this is right. Yeah, but I need to remove this here. Yeah,
That's the one I did.
I'm not sure if it's about 5.
I didn't check that.
No, okay, yeah, I
Might have been, I got 5.
yeah. Yeah, so it might be this, but this is right, but I don't think I get credit for that one. So 7, maybe I did.
Well, I mean,
No, I did, actually, so it must have been this one. So this one, Sir.
where are you going to take a look at this?
Oh, yes, yeah, let's do that. So, this is, I think this is perfect. So let me just, okay, now just tell me, where'd you get this from? This formula.
But, I have a
Okay, okay. So that's fine. And so, oh, now, here, other people were doing this. Why is this true? I mean, this is just not true. Right, so, what? Oh, no, that is true. No, that's right. Okay. So it's n 10 to infinity, that's 1/4. Okay. So,
that one might be a little bit of a mess.
okay, so between so that's 7, and then rotate. Oh, okay. What did you get? Yeah, I don't think that I think there's a mistake here somewhere.
Think so?
But I'm not sure. So run me through this. So it's 2x.
It's divided there.
Yeah. No, I think that's okay actually. 11, and then should have anything supposed to connect it. Oh. So okay. So tell me about this one.
Any connecting point has to be longer than 1 because this is the shortest distance.
Right, and then.
And this is the arc length formula.
Right.
And that's the Pythagorean formula.
Right.
And they're the same thing, and they're greater than 1. Everyone is.
That's greater. What's greater than 1?
The length.
Which happens to be the. What is it? You've already said it. It's the.
It's
But more, it's something about that specific one. It's the.
Pythagorean's constant.
So you need to show that for any function, the length is longer than this, and you've shown that. What about this one? This is the.
Oh, it's the shortest.
It's the shortest. Okay, so that's.
Yeah, I wrote that over here somewhere.
Yeah, I just wanted you to say it again. Okay, so 16.
Awesome.
So I want to ask you, what do you think I would need to work on more to do better? Because we need to do it all.
Right, no, yeah, so we need to meet too.
Okay.
So we need to meet about antiderivatives, and I'm just going to, yeah. So we need to find the time.
Okay, I can come on Tuesdays and you come on Tuesdays and
Yeah.
Wednesdays? Okay.
Yeah, I'm here Wednesdays now.
Okay.
So, but I'm talking about a week or so from now. I'm going to give you enough time.
Okay.
And basically, I'm going to ask you these again.
Okay.
Right. And I'm going to ask you to definitely do a power rule 1 and stuff like that. So.
Okay.
And then that's not a problem to have 20 questions on that. Okay.
Okay, so practice.
Yeah. Yeah. Just all the antiderivatives.
Okay.
sir.
What if I'm not writing on properties?
Oh, I should give some for chapter 7 or for
For the derivative.
oh, Spanish derivatives. We're talking about we're talking about the
So
pick you. Like,
pretty much
maybe you should even start
get
with
to this
these.
answer,
They
right? This
tell
is
you
the
what
answer,
you-
right?
They tell you what you should do. I'm going to ask you a bunch of these, and then I'm going to ask you.
But this is the answer, right?
I'm going to ask you these.
That's the answer. But we have to just show how you get to that, right?
So by working it out, you
Yeah, get to that.
I'm going to ask you these.
What's the
Maybe,
main one?
I'm going to ask you 1 through 12. You got to have 1 through 14. 1 through 14 is the whole.
Can you do it this one?
You get 14. Not including 6. Not 6. Not 8. Not 10. And not 5. All the other ones.
That's the power.
Yeah. Yeah. And not no. It stops at 14. Stops at 14. Right. Right, but in those, yeah. So those and then these. Ask you to substitute. 17, yeah, I can ask any of those.
That's the answer.
26. Yeah, no, 26.
But it takes 3 months. Right, but it's not even
Sir. I thought you were going to show me a tattoo, but that's almost like a tattoo. That's going to be there a while. It must be a fantastic story. Oh, no, that's not a good story at all. I thought you were like serving some wave or something on the coast of, like, no, okay. Yeah, yeah. Who said that? The doctor? That's so funny. I would have looked at it like it was crazy. But you're okay. You look fine. Okay. Yeah, okay. It just looks horrible. Okay, I guess. Okay, that's hilarious. Well, I see now the links that you're willing to go through to be here, so it's good. Wow.
It was the day after the morning. Like we left home after the exam. Like,
Yeah.
Playing went to Boston for
Yeah.
a customer, and then turned up driving. Somebody was just hammered. It was about 6 in the morning.
Oh no. And you were alone.
Yeah.
Okay. Okay. I'm glad you're okay. Right. That's so funny. Yeah. Oh, is the book? Let me see this book again. Yeah, I figured. Right. Yeah.
Yeah, this is all. Usually numbers are the whole. Google Chrome. That's what it's how it works out. All of the lines that have to pick out the problem. You call it big bang and then start to pick the thing. But that's good if you're good with your
Yeah, I don't know what the answer is, but I get
Something solving for you?
Yeah. So it's like if I'm practicing something and I get the answer, then I can check it. So just actually see if I'm getting close to something.
Oh, are we ready? I guess we are ready.
Pretty good.
Okay.
We're not ready.
No? What's left to talk about? I'll take any questions about integration by parts.
I want to ask about. I just want to ask, like, when you pick the U and the dv, how do
dv.
you exactly know which one to pick? Are you just?
Oh, so what will happen is that there'll be two functions that you have a choice of, right?
Yeah, the x or the l.
And that's a u or dv.
Okay.
Okay? And so you pick u in this order so that,
Oh.
It's
Okay.
similar like order operation, right?
kind of, I suppose, yeah. So it's L-I-A-T-E. So whichever one comes first before the other ones, that's the one you pick.
Okay, so you pretty much pick ones that look like that.
Well, so the functions that you are going to be given are going to be the product of two of these, and whichever one comes first here is the one you should pick to be u. So if you had a log times an algebraic, because L is before A here, you pick u to be the log. If you had an inverse trig times a trig, which sounds pretty sick,
You pick the
then you would pick the inverse trig.
for you.
Yeah, absolutely. I'm here to try and make sense.
If you had an inverse trig times the right trig, you might have a good day.
That's right.
So if you get two of the same ones, then you just have to take the chance with it?
Yeah, if you have a trig, if you have an inverse trig times an inverse trig, then all bets are off and it's extra credit, right? So,
And then when you get to the bottom step, almost the answer, then you might have to do substitution by u?
that's exactly right. It's all, then once you get to that last integral, it could be anything. You could use anything to solve that last integral.
And if it's a definite one, you would just substitute in your...
Yeah, that's what this is what we're going to do in the discussion.
Okay.
So in the discussion, we'll do a definite integral and be done with this. Okay, so what about now wanting to know, let's put this here. Let's put it here. Oh, well, let's move you up. Okay. So what do we want to know? The integral from, let's say, 0 to 1 of, we've already done every combination of this, haven't we? So let's say 3x times the natural log of x. Yeah, let's do something like that. Well, the natural log of x squared. Right? So if I'm being an ass, something like that. Oh, 0 is such a bad number here. At 0, the natural log is minus infinity. So let's say from that's completely improper. The integral from 1 to 2. So we find the antiderivative and we'll plug in 1 and 2 and subtract. X times the natural log, what does that look like? X times the natural log of x squared x equals 1 to 2. What's the area under this thing? All right, yeah, what's the area under there? du is 1 over x squared times the derivative of x squared. So it's 2 over x is right. Absolutely. Right. So that's almost, we can almost figure this out, right? This looks almost like a triangle, half the base times the height. Looks about 8. Right? I mean, if you just look at the triangle, right, here, look, half the base times the height. Right? So let's see if that's close to 8 or not. right? So, again, for some engineers, that might be enough, right? And then to go through the whole integral process. Okay, so u equals 3x. Whew! Follow your own rules when u equals the natural log of x squared. And dv is equal to 3x dx, right? And then du, we could have brought this 2 over, right? But if you don't see that, then you still get the same answer. v equals 3 over 2 x squared. So what happens now with this 1 and this 2? Well, we could go ahead and find an antiderivative all the way at the end. Just go all the way to the end, then plug in 2, 1, and subtract. Okay. Let's go ahead and keep the streak alive. The integral of u dv is uv minus the integral of v du, and this may be the last time today. U times v, 3 over 2 x squared times the natural log of x squared minus the integral of v, 3 halves x squared. Does this turn out pretty? Times du, it looks like it, 2 over x dx. Oh, even the 2's cancel. So that's 3 over 2 x squared, the natural log of x squared, minus the integral of 3, 2's cancel, of 3x dx. And then finally, 3 halves the natural log of x squared minus 3 halves x squared. And then we can evaluate that from 1 to 2. No big deal. And so then, by the fundamental theorem of calculus, the integral from 1 to 2 of 3x, the natural log of x squared, is equal to 3 halves the natural log of x squared minus 3 halves x squared, plug in the 1 to 2 and subtract, and that's the ballgame. Alright, so maybe that is around 8 or not. But you can plug that in and see.
What happened? Did you just forget that x squared in the first part? You know that up a little bit?
Oh, I did. Thank you.
So we could just evaluate.
Yeah, you plug in 2 and 1 and subtract. All right. Okay. Anything else about integration by parts? Like, I doubt if the exercises here could challenge us that much here. So that's the next section. Let's see what we have. They must have logged me out by now. If they have, then yeah. Let's see. Is it somewhere? No. That's the next one. Nowhere to be found. All right. Okay. We've beaten this topic to death, right? Are we done integrating by parts? Yes. Okay. I'll take any questions. I'll give some my math lab problems on it. Okay. 7.2 trig integrals. And so now, how do we integrate the integral of sine to the third x cosine squared x dx? That's a classic one. How do we integrate just flat out sine squared? How do we do that? How do we integrate secant squared x tangent to the fourth x dx? So we want to do these. Okay.
Use trig identities.
Yep, we're using trig identities the whole time. That's right. So we're going to turn all of these problems into U substitution problems just by using the identities. All right. So let us do a refresher. Oh, absolutely. So we'll do a refresher on the trig identities. The basic one
You good?
thank you. The basic one that is staple is that sine squared plus cosine squared is equal to 1. Okay. So, what'd you say? I never say refresh. So here's a remark, right? So the remark is, of course, that sine squared, we'll call it theta, plus cosine squared theta is equal to 1. And of course, the immediate consequence of that is that that implies, of course, dividing by, dividing by cosine squared theta, one has immediately that tangent squared theta plus 1 equals secant squared. So you can see that really you just need to know this one and all the other ones follow. Okay. So that if we wanted to know sine cubed times cosine squared, right, and the integral of sine cubed x times cosine squared x dx, then we'll simply remark that we want to change this to a U substitution problem. Now, we know, being experts at U substitution, is that if we had a ton of sines and all multiplied by one cosine, then we make U equal to sine, and then du is cosine, and it's right there, right? And that's exactly what we want to do here. So we're going to make everything in the sines and leave, everything in the cosines and leave one sign out there to be du, right? And so literally we'll be bullies about it. And so this is equal to, and I just don't care, the sine of x is right there, and it's my intention to make it du. If I do that, whatever I have left eventually must only be cosines. Right? So here we'll make it clear, we'll pull out a sine of x. With the intention of substituting. If that's true, then we're left with sine squared times cosine squared. We can do a lot of ridiculous things with that. The immediate thing we'll do is that this now we're changing to cosines using the remark. Sine squared plus cosine squared is equal to 1. And that immediately implies that sine squared theta is 1 minus cosine squared theta, and that's a way of changing. Again, this is just pre-calc, right? So you're changing all the sines to cosines. If you do that, we can substitute, and the game is over. I'll take questions about this. One minus cosine squared theta times cosine squared theta. I'm sorry, it's x. Cosine squared x times the sine of x. U is cosine, du is negative sine. There's a minus sign out front, and then now you substitute. We'll put that in red. Question number 4 in the exam. And then U equal the sine of x. Du is, I'm sorry, I'm losing it. U is cosine x. Du is negative sine x dx. This becomes a negative sine 1 minus u squared times u squared du. We'll multiply through and it's over.
well.
Please.
Where'd you get a cosine?
Wait, where? Which one?
You said u equals cosine x.
I'm going to make u cosine. And then that's 1 minus u squared times u squared times du with a minus sign out front. If I have a bunch of cosines times a sine, then if I just, that means I have a bunch of functions.
Oh, we're no longer doing by parts.
Oh, no, 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 no. Well, there's no reason to do by parts. All these functions are in the same family.
I would thought.
Yeah. Yeah. Minus the integral of u squared minus u to the 4th du, yawn, 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 yawn. Questions about that? Now I picked a nice one to start, right? Turns out that these the powers mean something, right? In terms of the ease in which it is to do these problems. Right? This is one of the pretty ones. What did it require? Why was I able to do this? I was able to do this because the power of what was even or odd. The power of blank was blank. Look at what I did. The power of sine was odd. I was then able to pull one out that made this even, but specifically it made it sine squared, and I was able to change it immediately to cosine. Okay? So this is what happens, this is what you can do, and there, for sure there'll be a table at some point, but this is what you can do when the power of sine is odd. Go ahead.
You said something previously in the slide about remark.
The remark is that sine squared plus cosine squared is 1. And then we haven't used the secant tangent yet, but we'll do that.
But why is it so significant? It's odd. Say it were sine to the 4th x, could you just pull out sine squared?
Right, but that I could pull out sine squared, but then what am I making du? So if I pull out sine squared, I need one sine to be the derivative, yeah. Yeah, I was wondering what you were doing. You're like raising your hand or something. I was like, what is that? So let's up the level. So then if I say, oh, I actually had some other ones, but let's hammer home this point, that indeed if I have the antiderivative of sine to the 5th x cosine x, see the problem with doing this, and actually to really hammer home the point, you know, I really don't care what this is. Let's make this 107. Yeah. This is why it really depends on the power of sine. If the power of sine is odd, you can do anything. Do that one.
You not simply reverse it for whichever one has the odd power.
Hey, I was about to say that, but I can sit down. And you can, no, you can get up, and then I can take a nap while you do that. That's perfect. That's right. I was just about to remark that do you really believe that if we switched sine and cosine, that something different would happen, right? So I can do the same thing here, and we'll do that in just a second. That if the power of cosine is odd, we can do that one, right? It's only just ridiculous if they're both even, right? If they're both even, we have to do all this other stuff, which we'll talk about. Full disclosure here, a lot of this has to do with the next section. Okay, when we do those problems, those inverse trig integrals, then a lot of the problems reduce down to problems that look like this. So it's important to be good at this so we can do stuff for the next section. Why are these trig integrals important? Obviously, any wave is expressed, Fourier showed this some time ago, any wave can be expressed in terms of sines and cosines. Okay, you would expect that we would have tons of sines and cosines multiplied by each other, okay, in order to represent waves in the best way. So, yeah. So those functions might be important, and then to find the total something, we would have to integrate and then invoke the fundamental theorem of calculus. So here again, we'll pull out a sine. Of x. This becomes the antiderivative of, and we'll just have to pay the price for whatever's left. The sine of x. What's left inside is sine to the 4th x times the cosine of x to the 107th power. And then now we'll remark, now with this extra step, that's a 4, but then we'll remark that that's simply sine squared squared. I don't think I need any more parentheses or brackets. Okay. And then we'll use the remark. That is 1 minus cosine squared x squared times cosine of x to the 107 times the sine of x, and then you make u equal to cosine. And so you've written everything in terms of cosine, and now at this point it's just about algebra. 1 minus u squared squared, square that thing, multiply through by u to the 107. Power rule it out, and then you have the answer. We'll do that in a second. Beat me to the answer. And again, as I said before, not thrilling material, not thrilling, but again, it gives you an idea of how to do these things by hand. One can imagine that when you're working on your complex problems, you'll need to do some manipulations. I mean, it is going to be true that when you're working through your complex problems, and this happens whenever you're modeling, you never get the pretty answer to start, right? But if you know how to manipulate things pretty effectively, you can get it to look pretty, or you can get it in a form that you can put it into Mathematica, right? You can get it in a form that's nice enough to put into your mathematical programming language. U is equal to cosine x, du is negative sine x dx, and then this becomes the antiderivative. There's a big old minus sign out here. 1 minus u squared squared times u to the 107 du minus the antiderivative 1 minus 2u squared plus u to the 4th times u to the 107 du, multiply through. This is equal to minus the antiderivative of u to the 107 minus 2u, we're just adding these powers, plus u to the 111 du, and as we'll take it out right through this one, minus 1 over 108 u to the 108 minus 2 over 110, which is 1 over 55, but we'll keep it at 110. 2 over 110 u to the 110 plus 1 over 112 u to the 112. And this for sure is the first time I've ever done this problem. Right? I've never had those as denominators before. That's the nice thing about real numbers. There's so many of them that you can never really do the same problem twice. 1 over 108, u was cosine. Cosine 108x minus 1 over 55 cosine of x to the 110 plus 1 over 112 the cosine of x to the 112th power. Right? This doesn't mimic any real problem, but You just work through it. Sir?
Doesn't the cosine 110 part become positive and the cosine 112 part become negative because the negative outside the integral?
Oh, that negative distributes. So this is here plus, minus, thank you. Plus, minus. Thank you. Okay. Questions about this? We'll go ahead and switch and do this in terms of sine, and then we can start doing the harder ones here. And I'll take questions about this. I'll hold off. We're still writing. Okay, so now you can imagine, I'll do it pretty quickly, that if we had the integral of, you know, we need to reverse what we've been doing. So we need the power of cosine of the odd. So let's say sine to the 6x times cosine to the third x dx, right? So now we're going to pull out a cosine and roll through it. Please go ahead and do that one. Thank you. Is that good? Yes. Oh, labor. Okay. Yeah. And how is your handwriting on this? Is it better than mine? Probably is. Yeah, you get to practice. Undoubtedly, his handwriting is better than mine, right? Yeah.
I'm also not holding it in my hand. Yeah.
That's true. That's true. I guess that's true. And you're not flailing about. My arms just do things. I don't even realize what they're doing. They just.
You're not going to podium for this room?
There used to be one. You had no idea. There used to be a desk that extended out this far, and that would be like right here. I don't know. It's just everything's gone.
I think they moved into the other room.
Oh, did they?
You should go
Okay.
see it back.
Yeah, I was about to say we need to declare war or something. But yeah, there used to be a podium, and I would just be relaxed. But the podium is just a crutch, right? People, professors. Yeah, but you know, people hide behind it too often, right? Instead of, it's much easier to use a chair like this. So, but no. Yeah.
You can just bend, slide.
Oh no, he needed it to stay. You're good, thank you. You're not the only one in the class. So. All right, so it's the same idea. Let's run through it. So we'll pull out a cosine. So this is equal to the antiderivative of, let's be uniform, right? So again, we're just being cosine x dx. It's my intention that is going to be the derivative. What's left is sine to the 6x cosine squared x, and then that is what's left. This is equal to the integral of sine to the 6x times, from the remark, 1 minus sine squared, and this one is over. Okay. I'll put it in blue. U is equal to, I think I'm catching my second wind now. This is good. U is the sine of x. Well, let's go to midnight tonight. U is sine to celebrate. Celebrate any average.
That's 3.
Okay. I'm sorry?
You put in 2 there.
I did, because I pulled out one.
Oh, so you...
Yeah, now remember, I pulled out one because I want that to be du.
So in the other one, you also put 1 up top?
I did. Make sure you got that in the notes.
Okay.
Yeah. Actually, we're ending early today to celebrate an A average. What did you say? All the drinks on you. Wow. He's talking about Sprite. Let me, for the record. Okay, that's right. U and sine x. That's right.
Yeah, you don't have to look at the computer for the recording to hear it.
That's right. No, but I can focus my voice just to make sure. If I actually turn, it resonates. Sprite, Sprite, Sprite. Yeah. That clear liquid you see is Sprite. U is equal to the sine of x, and then du is cosine x dx. That equals to u to the 6 times 1 minus u squared du, and then we work through this. Again, question number 4 in the exam. The first one, part A is going to have sines and cosines. Part B is going to have tangents and secants, and then that may be it. Okay, maybe part A will be, it might be 4 parts because I got to make things even and odd. Okay, so u to the 6th minus u to the 8th du. But as you can see, it's pretty straightforward. So 1/7 u to the 7th minus 1/9 u to the 9th plus a constant. Right, so, and then u is sine. So 1/7 the sine of x to the 7th minus 1/9 the sine of x to the 9th plus a constant. And it might not be so obvious. As a matter of fact, these are way more interesting. It is not obvious that if you take the derivative of this bastard that you get this. It's just not obvious at all. That's some real extra credit, right? Because it just involves all these trig identities, right? That you got to reduce this back to this, right? So notice how the answer, it might work out nice, right? But yeah, it's not obvious at all that you get this back, right? So I actually do want to see that. Let's try one of those. So I'll make that as extra credit. It's going to, I'm worried it's going to be some obscene like trig formula that you'll need. But if that's true, then it should definitely be extra credit. Okay, and I want to see it. So the extra credit is show, well, let's say just take the derivative of this. So take the derivative of this. All right, so I'm not seeing how to do this immediately, so that means a lot of points. So let me make sure I know how to do this. So take the derivative of this to get the original function. All right, so, right, and then, no, it's not obvious. It's not obvious. Let's go ahead and make it 6. It's not obvious to me. There's something you have to do that I'm not seeing. Okay, so, but it's going to, you're going to take the derivative of this, right? And then you're going to get something, and you're going to have to factor out. From the chain rule, they're both going to have cosine. You factor out the cosine, and then I think you can factor out a sine to the 6th, and then you're going to be left with something. It's going to work out. It's going to work out. Actually, I think I see it. So wait, let's make this for a 5. I know how to do it. I know how to do it now. No. It's actually not that bad. Oh, actually, wait. No, I'm going to leave it alone. I'll leave it alone. It's actually pretty easy. It's actually pretty easy.
Extra credit today.
What did you say?
You're hemorrhaging.
Yeah. But I'm not giving any more after. There's not a lot to. There isn't a lot to do.
There's so many to say.
What did you say?
There's so many points.
Yeah, I know, right? Yeah, I agree.
You're 14 points on the day.
14 points on the day? Okay.
Like 4 extra credits. Well, we've only got one.
at some point we want to take the test.
You should before the review before the test. So,
Is that right?
Yeah. Wait, the test is on the 18th.
The test is on the 18th of.
We've got 2 more weeks. Until
Yeah, I guess so. Yeah. So, yeah.
You get a pilot up today?
That's right. Right. Okay. So wait. So I guess we have to go the whole time. We don't even have that much time. Wow. Okay.
If we
So.
want to review on
Yeah. So we'll see. We'll see how we're feeling in an hour and a half. Okay. So that's a joke. That's a joke. That's a joke. No, it's too serious. It's too. I'm sorry. It's not funny. She's laughing. See. Okay. All right. So what happens when these things are even? Okay. So now the antiderivative of one of the first ones I said was this one, right? And again, it comes from sine squared is equal to 1/2. And again, this is a remark, so let's put it in red. So the remark is, so with even powers, we're stuck with these reduction formulas. So sine squared, I don't know why I made that blue again, but sine squared x is equal to 1/2 minus 1/2 the cosine of 2x. And cosine squared x is 1/2 plus 1/2 the cosine of 2x. Okay, so I'm not even asking you to memorize those because it's not clear what the proof of this is not obvious to me, right? So nobody knows the proof of these trig functions. You just remember them. They all have to do with the circle and properties about the circle and its symmetry. You do, though, get that sine squared plus cosine squared is 1. You just add these two. They cancel. 1/2 plus 1/2 is 1. Okay, so the whole point of this, of course, is that if you substitute this in, this one you can just do pretty quickly. Okay. So that the integral of sine squared dx, sine squared x dx, is equal to, by the remark, the antiderivative of 1/2 minus 1/2 the cosine of 2x, and then that one's no problem, right? And then when we start multiplying even powers, then it just becomes this big algebra problem, okay? The antiderivative of 1/2 is 1/2 x, and again, we got to get good at these. The antiderivative of the cosine of 2x is indeed the sine of 2x over 2, indeed, plus a constant. And then that's it. So then it's 1/2 x minus 1/4 the sine of 2x. That's a constant. Okay, so when the power is even, we have to, so when both powers are even, which is what we're about to do, then we will go ahead and work on something like that. The other one to remember that sometimes comes up is that the sine of 2x, remember that one? What's that?
I thought it was 1 minus 2 cos.
1 minus 2 cosine.
Something like that. There's a number of ways to do this. So it's 2, but this one's 2 sine x cosine x. 2 sine x cosine x. So there are a bunch of them, okay? Yeah, there are tons of them. So if you remember this one, these two, I think you'll be okay. Yeah. So that now let's do one. So well, I'll keep this slide here for just a moment, and I'll take questions.
Cosine 2x, 2.
No, it's not. No, if we want to know cosine 2x, we would look here to one of these, right? We would just solve for the cosine of 2x here. Cosine 2x is 1, I'm sorry, let's use this one. Cosine 2x is 2 cosine squared x minus 1. Okay, so there, again, there's just tons of them. But okay, so that now when we have these ridiculously even powered ones, right, then we have something like this. So if we have the sine of x to the 8th power, we'll just remark, well, that's the sine of x squared to the 4th, and then that's equal to 1, I'm sorry, that's equal to 1 winger. It's 1/2, right? That's equal to 1/2 minus 1/2 the cosine of 2x to the 4th power. And then we will raise that to the 4th power, right, and get this ridiculous thing with 1/2 the cosine to the 4th of 2x, right? And that's not 1 over 1/2, it's 1 over 2 to the 4th. So, and it's plus. So then that would be the last term here, but then we could write that as 1 over 16, and then that's the cosine squared x, cosine squared 2x to the second power, right? And then we can write that one as 1/2 plus 1/2 what? The cosine of what? What is it? Well, 4x, right? You double the angle squared, and then you square that one. And then when you square that one, you come down to cosine squared of 4x. And this is what I meant by reducing, right? And then that's the last term here with a constant in front. And then finally, that's 1/2 plus 1/2 the cosine of 8x. And then that one you can just integrate. Okay? So that's the hand. I'm doing a lot of hand waving. But that's what you do with big even powers, right? You just keep reducing all the way down, all the way down. This is part of the reason why we actually never have powers that are that high for the sines and cosines, because you can always reduce them down to just sines and cosines of 1 power. Okay. So if I have sine to the 7th times sine to the 4th, then I can definitely write that as cosine of 3x plus sine of 2x. I can reduce all the powers down to 1 single power. It's just that you might be taking the sine of 75x or something like, right, and it's going to be even, so you might be taking the sine of 84x, right, but you won't have any powers left. Okay, so the worst one I would give, right, the integral of, let's do sine squared, cosine squared. This is certainly not the worst one, but let's start with that one. Everything's even. We're not pulling out a sine or a cosine. We just have to reduce everything down. We'll do this in a couple of ways. We'll put the remarks down, and this is what we're going to use immediately. Right? We're going to replace all of these. Here are the remarks. The remark is, again, that sine squared. So the game plan is we don't want any powers. If they're even, we just want to get rid of all the powers. And here we've reduced that 2 to a 1. And the price we pay is we put a 2 in front of the x. But we know how to integrate that. That's not a problem. Right? So cosine squared x here is 1/2 plus, and we'll replace that. When we multiply them, we'll get another square, but again, we can reduce that too. As a matter of fact, I need to use a different letter. So I'm going to use the letter U, because we're going to be playing with x so often, it's better to use a different letter. So that's U, U, U. So these are called the double angle formulas. You double the angle in order to get rid of the power. Say it again? That is good. Yeah. But this is the only reason why you should be talking about them in pre-calc, right? When you talk about them in pre-calc, it's for this specific chapter. It's the integral of, and then it's just some algebra here, just doing some algebraic stuff. And you will multiply out. If you're observant enough, you'll see that the middle terms cancel. It's a minus b times a plus b. It's just a squared minus b squared. Right? There are no middle terms here. Okay. So things simplify pretty nicely. It's the integral of 1/4 minus 1/4 cosine squared of 2u du. So it's this times this, 1/4, this times that, plus 1/4 cosine 2u, this times that, minus 1/4 cosine 2u. They're obliterated. And then minus 1/2 cosine 2u times plus 1/2 cosine 2u is minus 1/4 cosine squared 2u. So again, no middle terms. How do we do this? Well, we use the reduction formula on this. This is equal to 1/4 minus 1/4 times, and then this is 1/2 plus 1/2 the cosine of 4u. Right? And then finally we can do this damn thing. I had this in terms of x, right? So I changed everything to u for some reason, I'm sorry. But it's the same thing. So it's just x. This is x. That's 2x. That's x. That's x. 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 If I only multiply everything out, this is 1/4 minus 1/8 minus 1/8 the cosine of 4x. And finally, and again, doing it this way, no power, 0 gone. That's the point. This is equal to the integral of 1/4 minus 1/8. Well, 2/8 make up a 4th, so that's got to be 1/8 minus 1/8 the cosine of 4x. And again, we got to get good at doing these. It is 1/8 x, and then minus 1/8, and then it's the sine of 4x over 4 plus a constant, and that's the game.
You have to, with the cosine going to sine, would it be negative sign?
The antiderivative of cosine is sine. The derivative of sine is cosine, so you go back, there's no sign change. There's no change in the plus or minus. Okay. Questions about these, right? So I think that's all the cases for sines and cosines. If you multiply them, the first thing you say, please let something be even. I'm sorry, odd. You need something to be odd. If it's odd, you pull out one. It becomes very easy. If they're both even, you have to do all this reduction stuff. On my math lab, I'm only going to give a couple. And again, the one you should try, of course, that I'm holding out on is sine to the 4th, cosine to the 4th. Right? Hopefully it won't be that long and tedious. Okay. So you should practice that one because, I mean, I don't want to give one that's longer. I mean, it just takes too long. Right? So I think that one is one to test you on. That's probably the test question. And so just do that one. Because it's not so long as to be unfair, and but at least it tests you a little bit. Questions about these, right? So now we've settled the product of sines and cosines. If you see powers of sines and cosines, then they're either even or odd if they're integers, and then you can go ahead and work it out. I should also make it clear that this here, where did we do it? Maybe it's up here. This here could have been negative. I mean, this literally could have been 3,270,000, minus pi. It could have been. The power of 107 in this whole example could have been anything, so it doesn't matter. This could have been in the denominator, right? So it could have been over cosine to the 107, right? So it has nothing to do with the power of this. It could be any power. It's about pulling this out and changing, right? So on the test, this is going to look absurd, but then it only tells you that you should be playing with that. Okay. So notice again, 107 has nothing to do with 107. Has everything to do with 5. All right. Questions about powers of sines and cosines. Secants and tangents. Antiderivative of, let's say, tangent to the 4th x, secant to the 4th x dx. What's the antiderivative of that? Now, what you could do is write everything in terms of sines and cosines, right, and see whether you get one of the ones that we know how to do. That's right. We could do that, but the problem with that is everything looks even, And so it looks like you might get it one of those long, difficult even ones. So we probably don't want to do that. All right, let's look at the remark. The remark is going to tell us what we want to do. The first thing is, and I didn't write this for the other one because it was easy, right? We know that the derivative of sine is cosine, the derivative of cosine is negative sine, so it's pretty easy to pull out one of them. Now I'm pulling out one of them because I want one of them to be the derivative of something else. Now I'm going to do the same thing here, but I need to be more careful, okay? Because if I'm going to pull out a derivative, then that means that I'm not pulling out just one secant, I'm not pulling out one tangent. So for the remarks here, I need to say a number of things. And the first one is that the derivative of tangent is secant squared. And the derivative of secant is secant tangent. And so before I was pulling out sines and cosines because I wanted them to be derivatives, I wanted them to be du's. If I have intentions of pulling out something here, I need to be pulling out a secant squared. I need to be pulling out a secant tangent. Okay, so you should not just be pulling out one secant. That makes no sense because du needs to be secant squared or du needs to be a secant tangent. If you're pulling out one secant, you better pull out a tangent with it, right? So that the whole thing can work. Which one are we going to pull out here? We're pulling out secant tangent. I think that makes it hard. Because if you pull out secant tangent, you're left with tangent cubed. So if you pull out secant tangent, your goal then must be to change everything else to secant. So you want everything else to be secant, and then you can make u secant, and then du is secant tangent. That's the goal. But that's tough if you pull out secant tangent here. Let's pull out secant squared. Right? The other remark, of course, is that 1 plus tangent squared is secant squared. We're going to use all of these. Okay, and so we'll put it in green. We're going to pull out a secant square x. Can you tell me what told me to do that? The power of blank was blank. The power of secant is even. That's really good. So the power of secant is even. Right, because then when you pull out 2 from that, that keeps it even. Let's do it. So if you pull out secant squared, the integral of, all right, let's just be demonstrative about it. I need that. And everything else phonetically has to become tangents. Just tangent, tangent, tangent. And it's because the derivative of tangent is secant squared. Okay? What are we left with inside? We're left with a tangent to the 4th times
1 plus tangent squared.
Absolutely, secant squared, right? But then secant squared is 1 plus tangent squared, so it allows me to write everything in terms of tangent. Right? So when you talk to people who've taken Calc 2 before, at least the sick ones, they're just like, oh, it was great because it was like a game. You just figure out all these antiderivatives. It was just like a game, right? 1 plus tangent squared. That was until we get the sequences in series. And nobody likes that one. Okay. Then u is tangent and du is secant squared. And so. So let u be tangent and work through the rest of it. All right. So again, it's just about reducing all of these tangents and secants into something that's really nice. So u to the 4th times 1 plus u squared du, and then we'll work through it. Let u equal tangent of x, du is secant squared. with our eyes closed, u to the fourth, 1 plus u squared du. I'm liking brackets today for some reason. This is equal to the antiderivative u to the fourth plus u to the sixth. This almost looks identical to one we just did, right? At least in terms of u, 1/5 u to the fifth plus 1/7 u to the seventh plus a constant. U is tangent 1/5 tangent to the fifth x plus 1/7 tangent to the seventh x plus a constant. I'll take questions. So that's when the power of secant was even. Power of secant even, life looks good. See what happens when they're both odd. We're good. Tangent to the third, secant to the third. What happens there? So let's partition all these cases. We did it for sines and cosines. You get powers of sines and cosines. If one of them is odd, the game's over. If what are the other cases? Right? That means both of them are even. And if they're both even, then we do all of that reduction. So sines and cosines are over. So for tangent and secant, we have, if the power of secant is even, it's over. And now we have the power of secant is odd, but we also have the power of tangent is odd. So we have to see whether we need tangent to be even or not. So we'll do this with a third and then with a 4 in just a second and see what happens. I don't think it's going to work if that's a 4. I think it's going to be a little bit harder. All right, so using this remark, it seems like now we're going to pull out a secant tangent and change all of those other functions to secants. Okay. Let's see if that works. And then when we go through this, we'll see what needed to be, what power in order to do this. Pull out a secant tangent. If that's true, then it's the antiderivative of secant tangent, secant x, tangent x, times something that we need to change to secants. What's left? It looks like tangent squared x times secant squared x. This secant's okay, that tangent has to go, right? And it has to become a secant. So it seems like in order to do this, the power tangent needs to be odd. The power tangent being odd really helps here because now we can't do the identity. If this was a 4 and we pulled out a secant tangent, then this becomes a 3 and we are screwed. Okay.
So we're going to use secant squared minus 1?
Of course, right? So we'll use the remark or a direct implication from the remark. Since 1 plus tangent squared is secant squared, that's supposed to be secant squared. This, of course, implies solving for tangent, that tangent squared x is secant squared x minus 1. Okay, and so then this becomes the integral of secant squared x minus 1 times secant squared x times secant x tangent x dx. And then it's over. Then you let u equal secant.
Is there another way to do that one? The tangent squared x and secant squared x. Could you put secant inside and take the power of 2 outside? Since tangent x and secant x is equal to secant.
I'm sorry, say it again? You do...
Put secant inside of there and take the power of 2 outside. So basically you're squaring secant.
So bring secant in here.
Yeah.
That's secant cubed. And then...
Because secant is tangent and secant, right?
Secant is... The derivative of secant is secant tangent. Yeah.
So could you put secant in place of the tangent squared x and secant squared x?
Here?
Yeah. Can you substitute secant in for that?
I did. So I'm replacing this tangent squared with secant squared minus 1, but you want to do something different.
Yeah, would you be able to do that?
I don't know exactly what it is, though. You want me to... I'm sorry, what is it?
Take that, since they both have the power of 2,
Yeah.
take that power outside.
I'll take another one. Wait. No, you have to show me what you mean.
Okay.
Yeah, show me later. Yeah. What you mean. Well, yeah, and that may very well work. But again, our game plan to hold the secant x tangent x and just be committed to changing everything in the secants. All right, so I'm gonna be bad. All right, I'm not even gonna write it. Okay. So 1/5 u to the 5th minus 1/3 u to the 3rd, but then u is secant, and so that is 1/5 secant to the 5th x minus 1/3 secant to the 3rd x. How did I drop the constant? Plus a constant. That's crucial. How can I write just one answer when there are infinitely many answers, right? I should get 0. I should get nothing. I should get 1 out of infinity. That's the credit I should get if I drop the C. I'm serious. That's right, right? The infinitely many answers, I write 1. How much partial credit is that, right? What did you say? I'll take questions about this. So I feel like there's a case that's missing that we just don't know how to do. I think that there's a case where you just have to do some wicked stuff that I wouldn't even ask you to do. Now we're saying that if this is now a 4, what do we do then? All right, but I'll take questions about this first. We have this. Tangent to the 4th, secant to the 3rd. How do we resolve that? Tangent to the 4th, x, secant to the 3rd x. Yeah. How do we do that? I think here we may have to write everything in terms of sines and cosines and pray. Okay. No, seriously. Right? Because again, we can see what the problem is. Let's try and pull out a secant squared. So we'll try what we have. So we'll try. Okay, so pull out secant squared. And we'll see what problems arise. If we do that, it's the integral of tangent to the 4th times one lonely secant that's causing a tremendous amount of trouble, because it is not, we have to make everything tangent, and now it's hard to make this secant into tangent alone. That presents a problem. So that's a problem. All right, so Cyclops. Cyclops not. Okay. And then let's try, if we pull out a secant tangent, I think we had already previewed what that problem is, right? If we pull that out, then we're talking about the antiderivative of tangent cubed x secant squared x, right? And then we're reducing both of those by 1. Oh, we might be able to do it. I think we can't, right? Because then we can change all of these to tangents, but how do we change all of these to secants, right? When this power is odd, right? So you can see that there's a serious problem, and then sad Cyclops returns. Yeah. Well, the problem is that you can't. So in order, if I'm making this du, then u is secant. U must be secant, and so that means I need to switch tangent cubed to only secant. Okay. But then, so I need to make tangent cubed in terms of secants only. Well, I can do some twisted stuff like, well, this is tangent squared x to 3/2. I don't know if I want to do that. I don't think I want to do that, right? So then it becomes, 1 I'm sorry, secant squared, and that's not so bad. Maybe we can just do that. You know, secant squared x minus 1 to the 3/2 power, right, times secant squared. But then it's hard to, you can't multiply it. I mean, you can't do anything here. Right? Then it becomes pretty hard. Right? Because then you make u equal to secant, and you get u squared minus 1 to the 3/2 times u squared. How do you integrate that? Right, maybe, right? But that's what I'm saying, that creates the problem, right? So now, the problem, the difficult one is the power of tangent even, the power of secant odd. Now, is that all the cases? When they're both even, we're good. It seems like when they're both odd, we are also good. Right. Is this the last case? Right.
What if secant is even and tangent?
So let's try that one. If secant is even and tangent is
Oh, we
odd.
just tried that.
Did we do that?
That's what we turned it into then.
If secant, no, we need to start there. So that's the problem. So what if secant is even? So we're saying secant to the 4th x tangent. You mean this one? Yeah. Can we do that? Let's investigate. Pull out a secant squared, and we're golden. Right, so if you pull out secant squared, then it's secant squared x times tangent cubed x, right, times secant squared x dx, and then you can change this to what? 1 plus tangent squared. Right, so that works. So what have we concluded about secant? If the power of secant is even, then we can do any of them, right? If the power of secant is even, we're good. Okay. So it's this one, odd. Well, I need to put this in black. So odd, even, difficult. Sad Cyclops. Okay. I think I'm going to make Sad Cyclops a recurring character. Now, so, but I mean, we're more resourceful than this. Now let's see what we can do with this. So otherwise we'll just make it extra credit. The antiderivative of tangent to the 4th, what was it? Tangent to the 4th, that's secant cubed. Was that the problem one? Yeah. Okay. Let's write everything in terms of sine and cosine. Right. So now with abandon, we're going to write everything in terms of sine and cosine. And hopefully it reduces down to something we can do. This is the antiderivative of sine to the 4th x over cosine to the 4th x times 1 over cosine to the 3rd x, right? dx. And again, it looks like we're screwed. The antiderivative of sine to the 4th x over cosine to the 7th x dx. Again, if this was odd, we would be able to do something. Right.
So there's no way to solve this problem?
Oh, I think. No. I think there's a way to solve it, but it's just not. It's not in a way that would be reasonable to ask on an exam. But yeah. But feel free. Go ahead. We'll make it some extra credit.
I have a question.
Please.
These extra credits, are we allowed to, talk with other professors to see, if they might actually want to do it?
Oh yeah, that's fine. I mean, whatever you write just has to be right, right? So I mean, I comb through those pretty meticulously. So I mean, just if you write something that's wrong, you get nothing. Just make sure it's right. Okay, so we'll make that 4 points. What is that antiderivative? And let's go into the book and see what explanation they give for handling that case. Integrating power product of tangent and secant. Strategy. N even, pull out secant squared. So N is the power of secant, M is the power of tangent. See, I think they left out the case. Right? They didn't even include it. Is this m even n odd?
Yeah.
Is it, so rewrite the even power of tangent in terms of secant to produce a polynomial in secant and apply reduction formula for. What is reduction formula for? Something that I don't want you to use.
It's right there. It's right there. Reduction formula.
Wait, where is it?
Expression form, one of the tabs.
Oh, okay. Reduction formula for says, oh.
I don't want to look at that.
That's right. Okay, so now we see what the problem is, right? So, yeah, so. How do you get this, by the way? What does this look like?
Question, I'll do extra credit and get that one blank.
Okay, that's right. Yeah, so that now you know why I'm leaving that one out. Okay, so it would seem that we need the power of n will be even, or the power of m will be odd. I'll take questions. All right, so where are we on time? Okay, I'll give a hint to what we're going to do next time, and then we'll end. Okay, so no, as a matter of fact, let's end. Let's end with that. Next time we'll do some inverse trig substitution. Okay, so look over that ahead of time. Again, just fantastic work on the exam. Keep it up. Don't get complacent. Right.